welcome. Today's first speaker is Alice Bezett. She has her PhD from the University of Otago in New Zealand, and she's right now working in my institute as a postdoc, supported by the Kempe Foundation. She has been doing a lot of finite temperature theory on those gases, a bit of fermions, and right now she's also involved in a project we are having on quantum hydrodynamics, and that's what she's currently going to speak about today. So, please.
Thank you. So this is some work that we've been doing in the plant, looking at hydrodynamic instabilities in condensate systems. In particular, two-component systems where you have an interface and kind of looking at the instabilities across it. Some other groups have been interested in this too. There's a Japanese group that does it, and also the army here is doing some work on it as well. Right, so here's a brief outline. I'm going to give a short introduction into the particular instability that we look at and some other related ones. Then we're going to look at the analytical model that we developed, which has a new feature of having surface tension in it, which hasn't been done before. Then we're going to do some numerical simulations of a two-component gas, and look at equilibrated systems and the Rickman-Mishkov instability cost stress. And then to finish off with here the numerics to the analytical model. Okay. So there's been a lot of interest recently in doing classical hydrodynamic cases in quantum gases, so in quantum BECs and also in quantum placement, I think. And the interest is, it's new because people want to see if there's going to be anything interesting that happens in a quantum case that wouldn't happen in a classical case. It's interesting to have BECs, obviously, because they're very good to tune experimentally. So we have a lot of control over the interface we use, which is very, very good. Right. So my talk is mainly going to be about the Rickman-Mishkov instability. Just draw a wee diagram. Start out by talking about the Rayleigh-Taylor instability, which classically you have a heavy gas here, a light gas here, and gravity pointing downwards. Now if the surface is perfectly flat, nothing happens. But if you have slight perturbation, you should end up with growth of the wave that then turns into these big mushroom shapes. And then eventually the heavy one comes down and light comes up. The Rickman-Mishkov instability is very closely related to this, except that you don't have the constant gravity. You have your two fluids, and then you have a shock, so a pulse acceleration across this interface. Because of that, it's a much weaker instability. It's a lot harder to see in our BEC systems. But it's still very important. I mean, if you're building a bomb or something, and you're going to have an explosion and you don't want your fluid layers mixing, then you have to take a lot of attention with this kind of thing. But yeah, the Rickman-Mishkov will give the same kind of shapes, hopefully, as the Rayleigh-Taylor gives. Right, so here is some work that's recently been done. This is a theory paper by a society group. They take a two-component BEC, so a BEC which has different spins, and then they use a magnetic field to push it together. So this is different from the classical case in that it's completely symmetrical. Okay, so they start with their ground state like this, with a bit of noise added. And as we evolve in time, you can see this sinusoidal perturbation growing on the interface. And it develops further into these mushroom shapes.
So, excuse me, how do you produce the shock there?
Sorry,
How do you produce the shock in this system?
These guys,
Yeah.
they don't have a shock, this is the Raleigh Taylor. So
Oh.
they just have a steady magnetic field pushing it. Okay. What was I going to say? Yeah, so they notice that they have a cut-off. For very short wavelengths, you don't see this because of the surface tension. It kind of inhibits the growth of that instability. That's one of the things we focus on in our model. We're going to look at the surface tension effect. So, we're going to have an analytical model which we develop only for the linear case, so only when we have this nice sinusoidal perturbation. When we have all the extra things, it's no longer going to be so valid, but should be kind of okay. So we start in our two-component system with the dispersion relation for the interface waves of the two components. So this term here is going to be because of our magnetic field, and also has the wave component. In the absence of this magnetic field, we just have the normal result, which is dependent on the surface tension, your wave number, density, and mass. So, if you have no magnetic field, your omega is always going to be real, so you never have instability coming. If there is some field, then for some values of k, you're going to get an imaginary omega, which makes this interface dynamically unstable. Okay, so to make our model, we say we're going to have an impulsive field, and we make it a delta function. Now in this case, we can rewrite the dispersion relation as the time-dependent differential equation given here. So then we have our pulse term, and this is our term that comes from having surface tension. Now when McMahon and Rishkov did this, they didn't have this term here, and so when they solved it, they got a linear growth of the perturbation. What we're going to get is if we integrate that previous equation before the pulse and then just after it, we find that just before the pulse we have these capillary waves along the interface, and straight after the pulse we have the same waves but with a different amplitude. So the physical picture is you have these waves on the interface that then get pumped by this pulse. So this pulse is amplifying the waves that you already have in your BNC. And you should get the result of a standing wave along the interface. That matches for a large enough impulse. That's quite hard to see in the BNC. If you have a pulse that's big enough to actually create this standing wave, you've probably gone and destroyed your condensate and your entire system in the process. So we don't take that flat interface as our starting condition. Instead, we're going to take a case where you already have the nice sinusoidal wave on your interface. And I'll explain later how we're going to make that. But for this initial condition, we can get to this equation here, which gives the amplitude of our interface perturbation after the pulse as a function of what it was before the pulse, and also this is reliant on the pulse size you use and the wavelength of the perturbation. Okay, so we now have something at least that we can compare with when we do a simulation. So, the basic procedure we're going to do is we're going to find a ground state for two coupled condensates, which will both be rubidium-87, but they'll be different spin states. Once we have that, we're going to make a small perturbation along the interface. Now, I use a small sinusoidal perturbation just to get things moving faster, but you can just use white noise and get the same results. We then add a very small magnetic field gradient. which kind of just gently pushes our two condensates together and starts forming the Rayleigh-Taylor instability. So we start getting this nice sinusoid. Once we have it at that stage, we turn off the field and just leave it. And this capillary wave is just going to evolve nicely, kind of going up and down. And once it gets to a nice maximum, we pulse it and see what happens afterwards. Okay, so here's our system, no surprises. We have our two coupled equations. They're coupled to each other here. I mentioned the sinusoidal perturbation. And when we want to make the Rayleigh-Taylor instability, we add in this term here for a magnetic field gradient, directed so that they will push towards each other. And this results in a nice capillary wave like this. Okay, so this is not just after the field has been turned on. I've let it go for a couple of oscillations, and this is the result. And you can see, I think it's quite interesting that this is not perfect. Even though we started with a perfect perturbation, it's got a bit messed up around the edges. But it's still quite nice in the middle, so all of the measurements we will make will do just in this central part.
So these are not two-dimensional solutions.
Oh yes, it's two-dimensional.
Do you feel that there is any difference if one goes to 3D or you're using basic frequency?
I think it is, because I'm using, yeah, if you have a tight track, I think it is using something. Okay, so we can measure the frequency that this capillary wave is oscillating at. The frequency that we get is larger in the centre than it is in the edges. It kind of slopes away to zero. And that is why you're getting this funniness. It's because everything is reaching its maximum at a different time. They're also very well behaved in the centre. The oscillations continue for a very long time, very nicely. On the edges, they kind of fade back. All kinds of nasty things. We also can see a lot of pass-through in the edges. If you look closely, you might be able to see kind of, maybe you can see it in here, little dots. That's from the condensate leaking through the edges at the start when we first turn the field on. Okay, now, we'll watch some movies. Perhaps. Okay, so there are three basic regimes that I'm going to talk about. The linear regime, which is just normal sinusoid, very well behaved. The non-linear, where the sinusoid kind of changes or becomes pinched in like this, and then non-linear with detachment. For a reasonably small pulse. So we can start with a nice capillary wave, which is at its maximum concentration. And as we go through, it starts, it looks like it might be linear, but keeps developing. And you can see this is no longer a sinusoid. In the end, you can see there's a lot of deformation in the area where there's no surface tension. Okay, so if we try something a little bit stronger, like so. Still you see that they haven't detached, but there's now a great deal of pinching in on these edges. You can see quite clearly how the different surface tension across the interface changes the behaviour of this particular instability. Right? Now, and finally, we have this one, which shows them actually popping mushroom shapes, which you see a lot in the rally tailor animation of instability. And then, of course, it's large enough to actually come off. Also, you can see this kind of bubble formations that's come up on the side, and there's a bit of mixing. As you get to higher and higher pulse strengths, you actually see that you can no longer see nice mushrooms at all. You just get this huge mixing layer, which I think they've seen in flame fronts, just this cascade of mixing. Okay. Our pulse that we apply is not a delta function in our neural simulation. We just use a Gaussian, but it's very, very short. Okay. So here's just a couple of shots from the movies. One particular thing I want you to notice here is this almost perfect spiral at the edge. This is what the kind of classical Hitchcock instability looks like. So you can see how much we've deformed it into the middle. Also, with these bubbles coming off here, you can often, if you have a very large pulse, get spikes with many, many bubbles coming off across on this head. That never ever happened for us. We always had far too much surface tension, and things that pop off very quickly get shoved back onto the condensate, and you get back to nice steady state.
Why the bubbles are not spherical? Surface tension kind of wanted tension to sort of, like you said, or because we were pushing them together or something as before.
I guess they're not perfect because they're not developing perfectly. Like they're trying to flatten out. And then
you have the trap as well, maybe. So the density is different.
Yeah, the density is different across interfaces.
And it's also moving, so I think if you have somehow moving against something which is repulsive, it probably gets flattened.
Yeah, this is true.
When you generate this complicated path, and how stable is the code? I mean, if you be around with the same condition, does it look?
Yeah, you get
It's completely reproducible.
almost exactly the same thing. Yeah, you can double the amount of grid points or whatever, and you still see.
So why does this spiral form on the right but not on the left? Why
It
is it
is
not
actually
symmetric?
on the left, but it's opposite.
Oh, but
So it's from the
kind of
other condensate coming around.
it looks different from the distance at least. It's like not quite the same. Left and right is not the same.
Yeah.
Maybe it's slightly not symmetric, although I think it's symmetric. But there is, there is a small amount of noise around here, which is always going to be not exact. So maybe that's affecting it slightly. Okay, maybe I should talk a little about the caps. Under these caps, you should have vortices. So we look at the phase of a single shot here. And if you look where it's pinching in just to come off, you can see that there is a vortex here on either edge, which is caused by the Kelvin-Helmholtz instabilities. You have two liquids passing by each other. You get this vortex formation. Another thing you can see from looking at the phase is that there are large oscillations within the condensate. I'll come back to that, but that's quite important. Okay. So we did a small calculation, seeing when it would be energetically favourable for a we got was that when this length here is about 1.3 times the wavelength of the perturbation, you should get it separating into a circle and a small hump. When we measured it close to the centre, we actually found that the result was closer to half away from it. But this is quite a simple calculation, and it was incompressible, which our system is not, and it also doesn't have any Kelvin-Helmholtz instability occurring along the edges. So it's okay with this. Right. So this is a graph of the equation I showed you at the start of the relative growth of the condensate, of the perturbation, versus the pulse strength. Now the line is the calculation analytically, and the dots we get from measuring the final growth of the middle peak of the perturbation. So this is our linear regime, where we're nice and sinusoidal. This is good. This part here is where you have the detachment of a bubble off the hump, and that actually also agrees quite nicely. But these results here, we just had deformation of humoral perturbation, are really quite awful. So we started to look at why that might be the case. I think actually, I go back to this video, and you can see huge oscillations in the system. But if you look closely, and I'll try and stop it about there. There was this extra wave coming back through that repulsed the interface. Right there. Okay, so our interface has been repulsed by something. So we have a look here at the oscillations of the system for our system which has the perturbation, and also for a system which has a completely flat interface. So these dots are for a flat interface where you don't have anything propagating through. And we see that there's quite a large width difference. The width of the Riemann-Roch system is much, much less, so I think they're seeing a lot of energy going through the interface from these oscillations. If you look at just one single run and actually study how it grows with respect to time, you can see there's a fast growth initially, and then it kind of stops, and then it starts growing, and then it plateaus again. And this corresponds quite nicely to when the oscillations in the condensate are squeezing it in. So when it starts squeezing it back in, so width goes down, oops, we get a growth. So if we then go and measure if we then say, okay, let's just measure that first spurt of growth and then stop, we get our results here in the squares. So our diamonds were what we had before. You see this initial growth actually agrees much, much better. Also, it's slightly below the line, which is kind of good, because you need to see that you have lost some energy to this oscillation. So in the end, we were reasonably happy with what was going on. Okay, I think that's all I have to say. So I showed you our analytical model, and from it you can see the influence of the equatorial rays, and also see some separation of droplets. And our numerical simulations agreed reasonably nicely with that analytical model, and we can also see a large influence on the oscillation of the components.
Do you allow vortex singularities in the simulation? vortex singularities in the Gross-Pitayevsky evolution? I mean, the odd parameter is continuous everywhere,
Yes, I think so.
but presumably in these Schwann propagations, you would get some vortices on the edges coming in, or
Oh, you mean on the edge of the simulation?
right? Oh, an interface there should be vortex where the surface becomes rough. Would that change? I mean, has it been studied or?
I haven't studied that, no.
Well, we do have vortices on the interface.
Yeah, but the pairs, right?
Pairs, yeah.
Is that what you were meaning?
Right.
Oh, yeah, we have the phase picture I showed. Oops. Yeah. Here, you can see, and you're getting vortices here and here underneath the caps.
Where's the interface? Or where's the?
Oh, sorry, this is one component here, so the interface is along there.
I see. So those pairs propagate into the bulk, or they, what do they do?
They seem to kind of just disappear. I haven't looked at long term behavior where they go, but the whole interface becomes stable again. So after it's finished mixing the layers. And we don't see anything fancy like them coming into the concept. It's purely a difference.
Kelvin Helmholtz instability, and there was some experimental work in liquid heating. I mean, has similar kind of experiments been done on these kind of instabilities in heating systems? Have you?
No, I think I just limited with carbon models. I haven't seen. No, I don't think I've seen them.
Any more questions?
Actually, I see the question. Can you show the equation you used? Let's say like df of dt. On the right hand side is the delta function of t. Because I missed the first part. Coming late. Sorry.
Oh, sure.
Yeah. In this equation, what are the assumptions? Because it looks like you have a. Are you separating two time scales? Like the power. So the dynamics of the fluctuation of the condensate will be quicker than the pulse, or the
Yeah,
other
so
around.
I think what we
To
do
make
is
sure
we
this
solve
equation
it-
valid. Yeah.
Like we solve it just before and
Uh-huh.
then just after. So we're not going.
So the pulse has to be. So the dynamics of the condensate should follow the pulse. So it's much quicker than the pulse.
The pulse happens, and then the condensate does its thing afterwards.
So when you do the pulse, the condensate, you can generate a lot of dynamical excitations, right? Are those times go faster than the pulse? Or you have just treated the pulse for the quantum
Yeah, I mean, the
dynamic?
pulse is so quick, you don't really see the condensate catching up to it at all.
Uh-huh.
You know what I mean? So you can see a very slight, I mean, not with the delta pulse, but with the Gaussian pulse that is, you can see a very slight kind of density peak trying to form. But then it's over so quickly that it just,
Mhm.
the system just continues.
Okay. If there are no more questions, let's.
So,
Yeah.
let me ask one more thing. So, in your equations, the Gross-Pitayevsky equations, you disregard any dissipation. So, would you expect, dissipation to dampen your instability somehow?
Yeah, it should do. But in a closed system, maybe that's not such a benefit.
What do you mean?
Well, I mean, I can assume that you don't lose anything from the pulse. I guess.
Right, but when the instability develops, dissipation will dampen it somehow.
Yeah, it will.
And then it's a question about time scales. Somehow this damping time scale, if it's slow enough, then the next question is how quickly these happen relative to the damping scale, and I guess in the BC normally the damping scale is so much longer. I mean, often you can ignore it.
Well, it depends on temperature.
Yeah, of course. Yeah.
I mean, if you have these capillary forces there, I would assume that if you have like small perturbations, they will probably don't grow because capillary force probably will prevent it to grow. Or do you see anything like that, or am I
So
wrong?
what do you mean?
I mean, if you have
So,
some small perturbation, which then capillary forces won't really let it to, you know, grow because of it.
well, I amplify it a lot with this magnetic field. So if you use a very, very small perturbation or like a white noise, it takes a very, very long time to actually grow it, which is why I used a sinusoid just to speed it up.
But can you say the threshold of the or what's the minimum perturbation?
I don't know the minimum perturbation. As long as you had something, if you wait long enough, you will get something happening.
I believe we expect that any capillary wave should be amplified by the same factor. Isn't that what we find? We haven't really tried it numerically. But even if it's small, it's still going to be amplified by the same factor. We don't think there is a threshold.
You know, if I have capillary force, I don't really want to get before in the first place, so I probably need to overcome some deformation or something. I may be wrong.
I have a qualitative question. In the Gospitayevsky, you can transform it to a classical hydrodynamics plus what's called the quantum pressure term, right? So what is the qualitative effect of the quantum pressure term? Because you're solving the Gospitayevsky, you have effects which are
But
non
the phase is quantized, so you have quantized forces. In classical hydrodynamics, you have non-quantized forces.
That's another effect of the quantum nature of the vortex. But just when you compare classical hydrodynamics to Gospitayevsky, there's
Yeah, we were discussing this
terms
before.
that become important when you have very strong gradients, which is exactly where the interface is. And did you study that?
I'm
What?
not sure. No.
You could just compare the two evolutions and see if you see different pictures. Like,
Well, I think most of the difference in the pictures that we see is due to surface tension, not due to some quantum effect. But I'm not completely sure.
Then is it important to have a BC at all? That's a big question.
Possibly not. It's a nice system to play with.
No, it's regulatory, of course.
Can you model turbulence in the system somehow if you apply, let's say, subsequent pulses, like one after another and after another, you mix everything up?
Get a really big mess. I haven't tried that, but I guess yeah, you could do that, pulsing that with stages.
Because it's much simpler than Navier-Stokes.
What's that?
Navier-Stokes equations.
Oh, okay.
So, might be a nice model, learn something about turbulence.